Hello everyone, my name is Qinglan. I'm a PhD student from the Aerospace and Mechanical Engineering Department of the University of Notre Dame. My topic is Neural Network Forward Model and Transfer Learning Calibration from Monte Carlo to Diffuse Reflectance Spectroscopy. I will first give a brief introduction to the background and then introduce the diffusion theory and Monte Carlo simulations. We then propose to use neural networks to learn and replace Monte Carlo simulations. Further, we apply the transfer learning method into calibrating Monte Carlo to diffuse reflectance spectroscopy. Nowadays, optical imaging has been widely applied in varying areas. It enables us to non-invasively detect circumstances in mediums. For example, in biological tissues like plant leaves, human skin, and animal brain. In biophotonics, because usually different components and different types of tissues have their own characteristic curves of absorption and scattering. Inversely, by detecting the light transport behavior in biological tissues, we could estimate the optical parameters and then estimate the amount of components or any abnormalities, for example, the amount of oxygenated hemoglobin or the location and size of a tumor tissue. The light propagation in turbine mediums is described by the light transport equation. Mu A, mu S, and G and phase function of the medium are the dominative parameters in this equation. The absorption coefficient mu A describes the probability of a photon being absorbed per unit length. The scattering coefficient mu S reflects the probability of a photon being scattered per unit length. Further, by expanding the diffuse radiance L and light source S in spherical harmonics and only keep the terms of order up to 1, we obtain the diffusion theory that describes the fluence rate phi. The anisotropy factor G is introduced, who is the cosine average of the phase function. Now the diffuse reflectance could be expressed as the equation at the bottom, which is proportional to the gradient of fluence rate. This expression connects experimental measurements with diffusion theory because the diffuse reflectance is a measurable quantity. By detecting R spectrally or topologically, inversely we could estimate the optical parameters mu A, mu S, and G. However, diffusion theory has drawbacks. First, diffusion equation usually holds only when mu A is a lot smaller than mu S. More importantly, the diffusion theory loses accuracy near the light source, as is shown in this figure. Therefore, frequently massive Monte Carlo simulations are needed. Monte Carlo has been used as the standard when investigating the light transport in turbine mediums. It is accurate and versatile. However, it could be inconvenient, computationally expensive, and time-consuming. Therefore, we propose to use neural networks to learn and replace Monte Carlo simulations. A sufficiently trained neural network with tuned hyperparameters is able to output results as a good approximation to Monte Carlo. Neural networks are easy to use. Once it's trained and saved, it will be able to make rapid predictions given new values of features. Neural networks are also very versatile. They could be trained with any new interested dataset and then be applied to the new task. We call the neural network that replaces Monte Carlo neural network forward model. To obtain the trained neural network forward model, Monte Carlo data with varying optical parameters is needed. We ran 1,750 Monte Carlo simulations whose mu-A, mu-S, and G are sampled in those ranges. The diffuse reflectance was probed and 10 source detector separations from 0.1 to 1 centimeter. The wavelength was fixed at 500 nanometers. The neural network was then trained with 80% of the Monte Carlo data. The performance of predicting the diffuse reflectance of the test data is shown in those figures. Each sub-figure shows the predictions for the diffuse reflectance as a corresponding source detector distance. The normalized mean absolute error is calculated when the true data is scaled into the range between 0 and 1. As we see, the normalized mean absolute errors are very small. This means that the neural network gives accurate predictions for diffuse reflectance in MC given mu-A, mu-S, and G. It is able to work as a reliable replacement for Monte Carlo simulations. Since Monte Carlo data is still needed to train the neural network forward model, it is reasonable to question how much Monte Carlo data is needed. Therefore, we have trained the neural network forward model independently with varying training set sizes. The total mean absolute errors over all source detector distances of the test data are shown in the figure on the left. The red dots at each training set size are the mean absolute error when training for 3 times independently. The black stars are the averages of the red dots. In the picture on the right, it shows the relative difference of the total mean absolute errors to the lowest value, which is at 60%. We see that training with 40 to 80 training data, that is 700 to 1400 Monte Carlo simulations, the total mean absolute error fluctuates within 20% to the lowest. As is also shown, less than 30% data, which is 525 Monte Carlo simulations, is obviously not sufficient for the neural network to learn the physics. We have also compared the time for the neural network forward model to make predictions and the time in Monte Carlo simulations. Time of the trained neural network forward model making different numbers of predictions is shown in the table. As listed, the neural network takes about 0.1 second to make predictions, and the time is almost the same for different numbers of predictions, up to 1500 predictions. This is because the neural network calculates the predictions for all given points of mu-A, mu-S, and G at once. The prediction time doesn't linearly accumulate. In the figure below, one Monte Carlo simulation takes from 12 to about 3500 seconds. Clearly, the trained neural network is a lot faster than Monte Carlo. And even considering the training time, the neural network is still a lot more time-saving. It is also necessary to point out that the time of either Monte Carlo or neural network depends on the computer they are run on. But because of the nature of the two, the difference should still be as significant as is shown here. Transfer learning is a machine learning method that reuses a model trained with one dataset to learn another related dataset by adding and optimizing some more neural network layers. Now, having the trained neural network forward model, we employ the transfer learning method to calibrate the diffuse reflectance in Monte Carlo to that measured experimentally. With some experimental data, we feed the known optical parameters into the trained forward model. It then gives predictions of diffuse reflectance in Monte Carlo. Then those predictions and the corresponding wavelengths are taken as the inputs of the second neural network. The second neural network gets optimized so as to predict experimentally measured diffuse reflectance. The advantage of transfer learning is it makes use of the knowledge it learned from the old data so that it usually needs less data to learn the new task. In our case, we expect the transfer learning model to be able to make good predictions for the experimental diffuse reflectance with a small amount of experimental data. In order to train the second part of the transfer learning model, experimental data measured with DRS is needed. 5 liquid phantoms were prepared by mixing polystyrene stock, hemoglobin stock, and water in different volumes, and then were measured with a DRS system. The mu-A was calculated according to the linear relationship between mu-A and the concentration of hemoglobin. Mu-S and G were calculated with me theory. From the phantoms P1 to P5, the absorption coefficient gets larger, the scattering coefficient gets smaller. G stays the same. Then the second part of the transfer learning model was trained with DRS data of 4 phantoms. Then it predicts the diffuse reflectance of the test phantom. We have switched data of which phantom to be used as a test data. Those 2 figures show the predictions of DRS diffuse reflectance of P3 and P5. And those 3 figures show the predictions when using the other 3 phantoms as the test data. As we can see, the predictions don't fit the DRS data perfectly, but the normalized mean absolute errors are in fact very small. We conclude that the transfer learning model is able to calibrate Monte Carlo to DRS data well with only a small amount of experimental data. The Monte Carlo data here could be either from the neural network forward model or actual Monte Carlo simulations. In our case, the Monte Carlo data in this calibration is from the neural network forward model. In concluding, our neural network forward model works well as an accurate, easier, and faster replacement for Monte Carlo simulations. It gives accurate predictions for Monte Carlo outputs rapidly when given new values of the optical parameters. The transfer learning model calibrates Monte Carlo to diffuse reflectance spectroscopy data well. It needs only a small amount of experimental data. The transfer learning process is applicable to calibrating different datasets, even from different instruments, without needing to run further Monte Carlo simulations. For future work, we'd like to apply the transfer learning model into solving the inverse problem. It could be more efficient since it's faster than Monte Carlo. We would tune the neural networks to improve the performance. We have worked with topological Monte Carlo data at a fixed wavelength. We'd also investigate with spectral Monte Carlo data instead. Thank you.